It's time for another drop-in on Math Reddit, and I'm going to try to do this before the dogs start barking when my wife gets home. Yesterday, there was a discussion about integration by parts, and so I thought it would be fun to just kind of give an overview of integration by parts. One of the people I'm working with in tutoring is in the midst of this right now at the start of Calc 2. So quick review, where does integration by parts come from? Well, it's just the backwards product rule. And in fact, if you don't remember the formula for integration by parts, don't worry about it, because as long as you know the product rule, you can crank out the formula for integration by parts. If you can write down the product rule and then integrate both sides, on the left, you're integrating a derivative, so that just returns to the original product, f times g, and then you have two integral terms on the right-hand side of the old product rule, which each mixes up an original function and a derivative, and we can tidy that up a little bit, at least on the left-hand side there, and then to get the integration by parts formula, we just rearrange it a little bit from this point, which I just copied from the previous slide, to this. Just take this term here and subtract it over to the left, but you're used to looking at it flipped around like this. And so this is the standard integration by parts formula. The integral of f times g prime is f times g minus the integral of f prime g. Or if you like your u's and your dv's, it's a little more compact. I like the full functional notation to just remind me about my dependencies and things like that, and to see my dx's. But it's the same formula in disguise either way, right? Integral of u dv is uv minus integral of v du. Okay, so how do you know when integration by parts kicks in? Well, experience, right? That's one thing. But generally speaking, if somebody throws an integral at you, and if you had been asked to calculate the determinant of the function, the derivative of the function involved instead, if you look at that and said, I probably need to use the product rule on this, then there's a good chance to do the integral of that thing. To go the other way, you might need to use integration by parts. So the way it works is you have an integral of some function that looks like a product of a couple of parts, thus the name integration by parts, and your job is to just pick and choose which of those two parts you're going to call f and which you're going to call g prime, or which you're going to call u and which you're going to call dv, depending on your notation, and then you're going to construct the other terms you need and load up that integration by parts formula. Integration by parts just turns, the idea is for it to turn a complicated integral into a slightly easier integral. It doesn't solve it directly. You still have to evaluate the second integral that you come across, but if it's used well, the second integral is easier. Okay, there are mnemonics out there to tell you which parts are generally good to look at to be, say, G or U or F or whatever, whatever language you're using. But I'm going to argue that you don't really need any of these mnemonics. Like one of them is IL, it's the inverses, logarithms, something, trig, exponentials, things like that. And those are, you kind of comb through those functions until you come across one, and then you make your assignments accordingly. I'm going to tell you a more loosey-goosey way to think about it. And the idea behind integration by parts is that you get to take one of these two parts and exchange it for its derivative. So if you have an integral with two parts, and in one of those parts you say, you know what, I could make this problem easier if I could take this function here and replace it by its derivative. And that locks you into which is your best choice for G, right? Or for U in either one of those, whichever one of the notations you're using. Okay. Now the trade-off of being able to exchange one of the parts for its derivative is that the other part is going to get traded for its antiderivative. And so there's a war there, right? One function's going to get a little bit less complex, but the other one's going to ratchet up. Now, which one leaves you better off? That's the choice. Okay. So the example that had this conversation around it looked like this. There was a particular constant, I think it was 3 in this place, but let's just leave the integral of x times sine of ax. Okay. So x and sine of ax are the two candidates for the parts that we have to assign. And so we kind of think through this cost benefit analysis. I could take the sine and trade it for its derivative using integration by parts formula, but that just trades a sine to a cosine. That's kind of on the same level of difficult. And the cost of trading sine for its derivative cosine is to go grab the x and raise it up a level to its antiderivative, which would be x squared. Okay, so that's not the choice I want to make. If we look at the x and we say, ooh, I could trade x for its derivative, and I'm just trading it for 1, a constant. The cost of that is to trade sine for its antiderivative, which would be negative cosine. But that change doesn't really do anything to the level of complexity of the problem. But changing x down to a 1, that's good stuff. Okay, so said all that stuff already. So using the f and g prime notation, we're going to say we would like to trade x for its derivative, and so we're going to assign f of x to be x, and then g prime ends up being sine of ax dx. Okay, so again, we're ready to solve the integral of x sine of ax dx using this integration by parts formula, and we have made the assignments. F of x is going to be x and g prime is sine of ax. And again, here's the kicker, right? Here's the original integral there. Here's the new one. We get to trade f for its derivative. F changes to f prime under the integral sign, but g prime has changed to g. And so those two actions together, you pick the best opportunity to simplify the integral. Then you get this extra term is just floating around there minding its own business. Okay, that really doesn't harm anything. Now with these assignments, f of x is x, g prime is sine of ax, then f prime is 1, dx if you want that there, and g of x is the antiderivative of sine of ax, which is negative 1 over a, whatever a is, cosine of ax. Okay, and then we plop all this new information into the template. The blue ones are the data related to f or f prime, and the red ones are just g at this point, because g prime is only sitting over here, the sine of ax part. Okay, now let's clean this up a bit. There it is from the bottom of the previous slide. Tidy this up. This term simplifies a little bit. Again, it's just there minding its own business. Here we get a positive 1 over a integral cosine of ax. The 1 over a can factor out. And now we've said, I don't want to do this integral. I'm going to convert it into this other integral, and hopefully this one is easier. And in fact, it is. The antiderivative of cosine ax is very straightforward, and there's the result. Okay, now I just threw in the plus c at the end there, and that's kind of standard procedure for indefinite integrals. We are treating antiderivatives all along, so there's sort of constants hiding in the background anyway, but just like with regular integrals, it's okay to throw in that plus c at the very end. You don't need to carry that baggage along all through the ride. Okay, so how about this one? Ax squared e to the bx. Okay, cost benefit. We get to trade either, we can forget the a, right, because that can get factored out of the integral. So we can trade x squared for its derivative at the cost of trading e to the bx for its antiderivative, or we can trade e to the bx for its derivative at the cost of trading x squared for its antiderivative. Now a trade of e to the bx for its derivative or its antiderivative is sort of a wash in terms of the level of complexity, right? So this is all about the x squared. Do we want to trade the x squared for its derivative, or do we want to trade the e term for its derivative, requiring us to upgrade x squared to its antiderivative in the new integral? Well, the antiderivative of x squared is x cubed, and we're still going to be retaining the exponential function. So we certainly don't want to convert this uphill into an integral of something related to x cubed e to the bx. Okay? So it's not about mnemonics, it's about just the cost-benefit analysis of the trade that you're about to make. So we've decided we would love to trade out the x squared for its derivative, so x squared becomes the f, the g prime becomes e to the bx. Let's fill in the rest of the data, or no, let's not. I didn't actually compute the problem, right? I forgot what I did on the slide before I turned on the recording. You can take it from here. Okay, this is the choice to make, and then what's next? Well, lots of bookkeeping, because when we use integration by parts to rewrite this integral in terms of one non-integral term minus this new integral, the new integral is going to be x to the first times e to the bx with some constants making noise on the front of that. So we're not going to be able to solve the end result immediately, but we have taken this integral of x squared e to the bx, we'll knock it down a peg to an integral of x e to the bx, and then integration by parts on that one will finally get us down to a level where we can resolve it straight out. So lots of bookkeeping. You've really got to mind your parentheses and your signs and things like that. Okay, the integral of t to the 10th, natural log of t, just to change the variable to keep things interesting. In this case, well, t to the 10th, man, that's horrible. So surely we would want to replace the t to the 10th with its derivative, right? That would be the choice for f. Well, no, because the choice of wanting to trade t to the 10th for its derivative through integration by parts will require us to trade natural log of t for its antiderivative. And what the heck is the antiderivative of natural log of t? Well, if you don't know it, the way you find it is through integration by parts. Okay, so this is a little bit counterintuitive. We would like to trade the natural log term for its derivative, which is only going to be 1 over t. Now the cost of that is then in the new integral we're going to be dealing with a t to the 11th, the antiderivative of t to the 10th, but that's okay. And if you work this problem through, the derivative of natural log of t is going to help cancel one of that new power in the t to the 11th. Okay, so it all works out. It all works out. It's good stuff. All right, here's a case that everybody has to go through at least once, something similar to this one, probably with more noise concerning constants either in the exponent or inside the trig function or maybe out front, but this is the stripped down bare bones version of this problem. It could be e to the x cosine x, or it could be e to the x sine x. This is like math black magic, where we find out what the integral is without ever actually solving the integral. It's pretty cool. Okay, there is no good choice about what to make f and what to make g prime. Whichever one of these things we trade for its derivative, we haven't altered the level of complexity of the integral, and whichever one trades for its antiderivative, we still haven't traded or changed the complexity of the problem. We're trading e to the x for e to the x, and we're just bouncing back and forth between sine and cosine for the other part. So we just have to make a choice to get this started. So we're going to let f of x be e to the x and g prime is cosine x. That means f prime is e to the x and g of x is sine of x. Okay, and integration by parts gives us this reconstituted integral where the integral of e to the x cosine x is a term sitting there minding its own business minus this integral of e to the x sine of x. So we have gotten nowhere, right? Well, let's take a look at this integral. Let's just set it off on its own and let's do its thing. We're still going to make the corresponding choices. F is e to the x, g prime is sine of x, and then this integral, according to the integration by parts formula, is another term minding its own business, plus integral e to the x cosine x. Now that one looks familiar because that was the integral we started with. We just went in a big circle, but we went in a big circle in a good way. Okay, here was the original intermediate step after that first integration by parts. We've now discovered what this term looks like, so we can plug it in there. We can shake out that minus sign through the parentheses, and now we have one instance of the original integral on the left and minus that original integral on the right, which means that version on the right is ready to get added to the version on the left. And we can divide by 1/2, and now we have discovered the result of the integral of e to the x cosine of x dx without ever having actually resolved the integral of e to the x cosine of x. We sort of sneak up on it sideways, but again, that's pretty cool. Okay, and here's the second weirdo case I wanted to point out. This particular integral, and there are others much like it, they don't look like they're suitable for integration by parts right off the bat. Okay, there's only one thing there, so how can you come up with two parts? Well, remember that there is a ghost multiple of 1 in front of any function. So we actually do have things that can play the role of the two parts. We've got the 1 and we've got the natural log. So which one of these two parts would we like to trade for its derivative? Well, with the 1, if we choose that as the part that we're going to trade for its derivative, well, that derivative is 0. Right? And so the new integral involving that would certainly be simple, but it would not help us solve the problem. On the other hand, wouldn't it be awesome to just be able to take the natural log of ax and replace it with its own derivative, because that's just going to be 1 over x. And that's certainly better than natural log. Now, the price of trading the natural log for 1 over x is that we're going to trade this 1 for its antiderivative, which is just x, but x times 1 over x, easy. Okay, so if you do follow this through with integration by parts, where this is the g prime and this is f, f is natural log, we're going to trade that for f prime in the new integral, that will work out. So get out a piece of paper if you haven't done this problem before and give it a shot. Okay. And here's another one just kind of like that, right? Finding the antiderivative of the inverse tangent function. Well, there's that ghost 1 again. We certainly don't want this red 1 to be f, because we don't want to trade it for its derivative of 0, because that just kills the whole problem. So we would like f to be the inverse tangent function. Now we get to trade that for its derivative in the new integral. You have to remember the derivative of inverse tangent, but that's 1 over 1 plus x squared. So we're going to be integrating at least a 1 over 1 plus x squared, but we're also going to be involving the antiderivative of this red 1 in that, which is x. And so we've got x over 1 plus x squared in that new integral, and that's a u substitution problem. So this one does work out as well. Give it a shot by kicking out that inverse tangent and replacing it with its derivative. If you have definite integrals, it's exactly the same process. You just have more bookkeeping because you're going to transfer the limits of integration from the old integral to the new one. And this one term that in the other problems just sits there minding its own business once it's created, you are going to have to evaluate it with those limits, just like the other part of the integral once it's done. So it's just more bookkeeping and more noise from numbers flying around, but it doesn't increase the complexity of the problem at all. All right. That was a quick journey through integration by parts.